Good afternoon. This is Jennifer Reynolds. I'm with the South Florida Water Management District, and I want to thank everyone for joining us today for our Aquifer Storage and Recovery Science Plan public workshop. We have over 100 people joining us today, and so we're giving everyone just a couple of more minutes to get connected. We are doing this workshop in conjunction with other agencies to include the U.S. Army Corps of Engineers, and we'll give Tim Geisen from the U.S. Army Corps of Engineers a couple of moments after I make some opening remarks in order to make any additional opening remarks from his side. But let me tell you a little bit about why we're holding this meeting today. Although ASR technology has been used successfully in Florida since the 1980s, some concerns have been raised about the large-scale application of ASR as it was envisioned in the Comprehensive Everglades Restoration Plan. So in 2015, the National Research Council reviewed our ASR Regional Study Technical Data Report and prepared a report of their findings. That report included information about how ASR would be used in SERP. And it said that we should move forward in a phased implementation, but that we needed to continue to address some remaining uncertainties. And to address those uncertainties, the Water Management District and the Corps developed this draft ASR science plan in order to describe the potential studies that would be needed and conducted in order to implement ASR wells in a phased manner. And so it works hand in hand with a phased approach to the construction of wells and to implementing what was envisioned in the Comprehensive Everglades Restoration Plan. So this science plan has been developed with review and input by an independent peer review panel, and many of you who are on the call today participated in our earlier workshops where we included dialogue with that panel and are looking forward to reviewing and hearing your comments about how we've included your comments as well as the comments from the peer review panel in our current draft. The studies proposed in the ASR science plan are intended to be conducted at ASR locations identified in the Lake Okeechobee Watershed Restoration Plan implementation, and they have broad application beyond just the scope of the Lake Okeechobee watershed. And so these studies have value anywhere that ASR wells are proposed and can be used to address ASR uncertainties associated with other programs as well as SERP programs. And the report is currently in draft form and it's undergoing technical editing. The report will be made available in its completeness for public review in January. And concurrent with the public review, the science plan will also undergo a technical review by the Corps of Engineers. And so with that sort of introduction, we'll get into the meat of the meeting. Since it looks like we have everybody joined now and all the numbers have stopped clicking up, I'll also just give a quick introduction to the meeting format that we have for you today. We've found that with webinars, there are benefits to holding questions and discussions to the end, and that's how we will proceed today. We have about 50 slides to present. We'll try to keep it moving so that we can get through all of the information for you and then hear your comments and questions. So we will have that Q&A available through Zoom for you to type in your questions as we go through the slides. So anytime during the presentation, if something comes up, please take the time then to type in your questions. It gives us an opportunity to see what your questions are and maybe even be able to address them during the presentation before we get to Q&A. We will review your questions following the presentation for any that haven't been answered during the presentation. We will also open it up for public comment. In the interest of allowing everyone an opportunity to speak, each person will have one 3-minute period to state their comments. With that, I will turn the floor over to Tim Geisen for his opening remarks.
Thank you very much. Really appreciate the opportunity for everyone today to participate in this public effort. I think the ASR science plan that the team has developed in draft format goes a long way to answering a lot of the uncertainties that folks have on ASRs. We've heard a lot of good things about ASRs, but also a lot of questions on the application at such a large scale. And I think the science plan really does a good job of trying to address all of those uncertainties. And we look forward to all of your participation, your feedback as we work to finalize that science plan. Because this really is an overall team effort, not only with the Corps and the Water Management District, but also all of the stakeholders in the state of Florida who will benefit from this application. So thank you very much, and I'll turn it back over to Bob to get started with the presentation. Thanks.
Okay, well, good afternoon, everybody. I'm really glad that we've got as much interest as we do in this science plan. And what we thought we would do today is structure the presentations. We've broken them up into essentially 3 different modules. And that way we can kind of keep everything separated, or at least parsed out for your understanding. Module 1 is a little bit of background about ASR in the Everglades restoration and the pilot projects that we constructed and tested, and then merging into the ASR regional study and the results from the ASR regional study. And all of that work was pretty much concluded in 2015, or thereabouts. Module 2 then brings us up to date with the Lake Okeechobee Watershed Restoration Project, and how ASR fits into that project and what has essentially prompted the development of this science plan. And then Module 3 really digs deep into the details of the science plan and the various tasks that we've developed to try to address the remaining uncertainties that have been elucidated by the National Research Council. And then at the end of the meeting, we're going to open it up to public comment and have some dialogue. So without further ado, I'm going to introduce you into essentially the history of ASR as it was envisioned in Everglades restoration. And of course, that brings us back to 1999, the Yellow Book, which had a whole variety of projects and components. Among them were 333 ASR wells that were envisioned to work in conjunction with reservoirs and surface features. Of the 333 ASR wells, there were going to be 200 associated with Lake Okeechobee. About 44 ASR wells were envisioned within the Caloosahatchee River Basin. And then another almost 90 wells that would be situated within generally the lower East Coast planning area. And of course, this was quite an unprecedented scale of the use of ASR back in 1999. And as a result of that, within the Yellow Book, they had authorized the construction of pilot projects in an effort to try to acquire data on the feasibility of ASR at this scale. And in order to organize how the ASR projects would function and what their objectives were, there was actually an issue team, an ASR issue team that was organized back then. And they formulated essentially 7 essential questions that the ASR program needed to address. And that was specifically characterizing the type of water that would be source water that would be recharged into the aquifer, characterizing the hydrogeology of the areas where ASR was envisioned, analyze the potential for rock fracturing and changes in groundwater flow patterns and rates, and to look at the changes in water quality that would take place when the water is stored underground. Back then, there was quite a large concern about methylmercury, so there was specific questions about addressing the potential for mercury accumulation, and then also to determine the relationship between recovery and recharge, and essentially the efficiency of conducting aquifer storage and recovery. So, charged with having to address those 7 essential questions, what we did was we developed the pilot project plans. The idea being we were going to go out and construct ASR systems to do to answer all of those questions. And after formulating the plan for those pilot projects, we actually engaged the National Research Council to review the plans for the pilot projects. And when they did, they published the first report back in 2001. And their essential conclusions from that report is that beyond the ASR pilot projects, we also needed to conduct a much larger, comprehensive understanding of what the implementation of ASR would be throughout South Florida. And essentially, they recommended that we create an ASR regional study. So we formulated the plan for the ASR regional study, and we submitted that report to the National Research Council, and they published their review of the plan for the ASR regional study back in 2002. And they actually, as a result of that, they made additional suggestions for tasks and studies that we did include in the ASR regional study plan. So way back when, we actually did have 2 National Research Council reviews of the plans that we were making for the ASR program. And what we did was essentially created 2 parallel projects. We, underneath the ASR program, we did implement the ASR pilot projects where we went out and constructed wells and systems, but we also developed a whole series of studies that would eventually become the ASR regional study. So a little bit about the ASR pilot projects. What we did was we went out to, on the map, the map on the left shows a bunch of red dots and black dots. We went out to each of those areas and constructed some exploratory wells. And we began developing designs for pilot project systems at each of those locations. After constructing the exploratory wells and the test systems, we actually wound up only having funding to be able to complete fully 2 ASR pilot projects. One ASR pilot project on the north of Lake Okeechobee along the Kissimmee River, and the other pilot project along the Hillsborough Canal down in Boca Raton, the ASR pilot project at the Hillsborough Canal. And the focus of our discussion today centers largely around the area of the Kissimmee River ASR pilot project, because that is the area where the Lake Okeechobee Watershed Project has been under formulation most recently. So here's a picture of the Kissimmee ASR pilot system. On the left-hand side, what you see is an intake structure out in the canal. That's the C-38 canal, which is just north of Lake Okeechobee. There's a pump system that pushes the water from the canal through a filtration process, a large sand filter essentially, and then across a UV disinfection system, and then into the ASR well. That's the blue piping at that facility. And then when we recover the water, we take the water out of the well, we pump the water out of the well, and push the water across that stair-step concrete staircase looking thing to have the water go back into Lake Okeechobee. And it turned out actually to be a very successful ASR system that we can talk a little bit more about later. The map on the right is a map of the monitor wells. The ASR well is located there and as a green dot. It's completed about 1,000 feet underground in the upper part of the Floridan aquifer. But in addition to the ASR wells, we also completed several monitoring wells in the same aquifer zone as the storage zone of the ASR well. And you can see where those monitor wells as the red dots are, and they enabled us to look at where the water went when it was pushed underground. And we were able to accumulate all of that information and ultimately published a pilot project final report. And a little bit more about the Kissimmee ASR system. We conducted 4 successively larger test cycles where we pushed water into the aquifer, we recharged it into the aquifer, we let the water sit in the aquifer for some period of time, actually ranging from 1 month to almost 6 months, and then we recovered the water from the ASR system. So that's what the graphic on the left shows, is the successively larger volumes of water that we pumped into and out of the well. And that 4th cycle, the largest cycle test, we pumped nearly 1 billion gallons of water into the ASR well, and we were actually able to recover nearly 100% of that water. So no question about it, it was a very successful test system. In addition, we were able to show or demonstrate that ASR wells were able to be pumped at 5 million gallons a day, very high capacity wells, very efficient capacity wells in the upper part of the Floridan aquifer. So that's a little bit about the Kissimmee ASR pilot project. And then in addition to the pilot projects, we conducted the ASR regional study, which was very, very broad in scope. The map on the left actually shows all of the wells, all of the well data that we were able to assimilate and formulate into a very comprehensive understanding of the geology of South Florida. And we were able to build aquifer groundwater models and to conduct ecological evaluations. And all of that data was then essentially tied to the results from the pilot projects. So we were able to calibrate the model results and all of the ecological results from the ASR regional study by tying it to the pilot project data. And a little bit about the groundwater model that we did develop. It was a very, very comprehensive South Florida-wide geologic model, including multiple layers of aquifers, the superficial aquifer, the intermediate aquifer, portions of the upper Floridan, middle Floridan, and lower Floridan aquifer zones. The model was then discretized into an entire array, a 3-dimensional array of all of those geologic boundaries and layers, and we were able to simulate what would happen in South Florida if in fact we were to operate what could be 333 ASR wells throughout the state. And the results essentially of the groundwater model evaluation were that we in fact could not construct 333 wells without inducing bad things within the aquifer. And what we did was we put several constraints on the model. For instance, we did not want to induce fracturing in the formation. We did not want to have excessive wellhead pressures. We did not want to induce saltwater intrusion or upconing of poorer quality water within the aquifer. We did not want to impact nearby existing users of the aquifer. And we did not want to have any impacts on areas in counties where there were reduced threshold levels. So when we put all of these constraints on how many wells we could pump, we actually had to ratchet down the number of wells in total. And the number ultimately came out to about 140 wells were doable in South Florida. And the map on the right shows all of those locations where we had inserted ASR wells. All of the colored boxes on that map show where the well locations were simulated within that groundwater model. And of the 140 total wells, about 80 ASR wells could be constructed and operated safely in the area of Lake Okeechobee. And it's that number, 80 ASR wells, that was ultimately carried forward into the Lake Okeechobee Watershed Restoration Project as a result of this regional groundwater model. So that's kind of how we got to the numbers of wells and how that was formulated. Now, in addition to how many wells we could construct and operate physically, we also wanted to evaluate what would be the impacts of that water that we recover from the ASR wells, right? The idea being that the ASR project would be recovering water that would have been stored underground, and we wanted to assure that there would not be any long-term detrimental impacts to the health of Lake Okeechobee or other areas where that recovered water ultimately could wind up. And we bundled all of the risk assessment work, all of the environmental and ecological studies into a very comprehensive ecological risk assessment. And the essential findings of the ecological risk assessment were that the likelihood of ecological harm to Lake Okeechobee and the Everglades is very low, primarily because the ASR wells would only be used intermittently, recovering water during times when there was a dry period that would not be a continuous use. The risk to fisheries was considered low, with some degree of uncertainty. Impacts to larval fish or entrainment of fish was considered moderate, with some degree of uncertainty that could primarily be addressed through design evaluations of the intake structures. And essentially, a recommendation of the risk assessment was that ASR systems should be constructed where areas where there could be sufficient dilution of the recovered water, but there was some concern, or at least that finding warranted some additional study. The bottom line results of the ecological risk assessment were that ASR is viable, but implementation should be incremental and geographically dispersed. So when at the completion of the ASR pilot projects and the ASR regional study, the findings of the entirety of the ASR regional study were that really there were no fatal flaws uncovered that would limit the use of ASR. Large capacity ASR wells can be built. However, because of some uncertainty with hydrogeologic areas, it's prudent to construct exploratory wells first. Water recovered from the ASR wells did not show persistent acute or chronic toxicological effects. The potential for methylmercury is low, but sulfate in the recovered water should be monitored, and that further implementation of ASR should proceed, but in a phased approach. So that was the findings of all of the work that we had done previously for the SERP ASR program. And that was pretty much all completed by about 2015. And what we're going to do now is change gears a little bit and bring the group up to date on where we stand with the Lake Okeechobee Watershed Restoration Project. And with that, I'm going to turn the microphone over to Jennifer Gent, who is the project engineer. Jen?
Hey, Bob, this is Liz. Jen is actually having some technical difficulties on her end. So are you able to cover her slides?
Sure.
And if she's able to get back on, she can chime in.
Okay. So the Lake Okeechobee Watershed Restoration Planning Area is an area that focuses on the watersheds essentially north of Lake Okeechobee. The actual map on the left shows the planning area, about 900,000 acres, focusing primarily on trying to look for storage north of the lake. The watershed has historically been documented or dominated by prairies and wetlands. And current land use in this area is there's a lot of agriculture, although there's a lot of natural area, open water and wetlands in this vicinity. And there is some very light urban and infrastructure that also is throughout this area. And really, for the last several years, the project team has been formulating what can be done, what series of components could be designed and built to address all of the project objectives in terms of better managing the level of Lake Okeechobee and better managing water discharge to tide and creating more storage in the area and water supply benefits. And this map shows essentially the recommended plan for the Lake Okeechobee Watershed Project. And the plan is broken into three different major components. The blue feature on the map area is a shallow above ground wetland attenuation feature. It's about a 4-foot deep impoundment, about 13,000 acres, and would allow us to have about 46,000 acre feet of storage in that surface reservoir. The circles that are on the map represent clusters of ASR wells, and they would be essentially constructed along canal right-of-ways that would be able to capture water coming into Lake Okeechobee or coming out of Lake Okeechobee. And those clusters might conclude, each individual cluster might consist of groups of ASR wells, maybe between 5 to 10 wells per cluster, and summing up to 80 ASR wells. And in total, that ASR component would allow us to be able to store almost 450,000 acre feet of storage per year if all of those wells were actually operated simultaneously for an entire year. And then the other component of the project are those green areas that are along the Kissimmee River and the C-38 Canal. They're areas that are former floodplain areas and wetlands that are adjacent to the river channel. And both areas, the Kissimmee area and the Paradise Run area, would consist primarily of wetland restoration features. So this project, the Lake Okeechobee Watershed Project, has been moving forward, and right now there is a project implementation report that describes all of the formulation that's gone into that array of features for the project, and it's been moving its way up through the review channels at the Army Corps of Engineers at the federal level. And while that has actually been happening while those reviews have been ongoing. The Florida legislature decided to give an appropriation to allow the South Florida Water Management District to accelerate construction of some of the features for the Lake Okeechobee Watershed Restoration Project. We received a $50 million appropriation in fiscal year 19, and then we received an additional $50 million in fiscal year 20. And specifically, those state appropriations were for us to design, engineer, and construct components to achieve the greatest reduction in harmful discharges to the estuaries. And what that really spelt for us is constructing the ASR component of the project. So what we've done now is created an incremental phased approach for the ASR program, looking at those ASR wells that are along canals that would ultimately allow water to flow into Lake Okeechobee when that water were not to be desired to go into Lake Okeechobee or ultimately discharged to the estuaries. So that is the ASR program that is embedded within the Lake Okeechobee Watershed Restoration Project. And as a result of that accelerated aspect, as a result of the state appropriation, that really has prompted us to formulate what is the ASR program that we've been moving forward with now. So what we've been doing when those appropriations were given is we have now focused on the area and those ASR clusters that are located north of Lake Okeechobee. And the red circles are those clusters that we are looking at most closely right now and in fact today. Within those clusters, there are 2 yellow stars, and those stars represent existing ASR facilities that already had been built. The star near the letter A is the Kissimmee ASR project that we already spoke a little bit about. The star in the circle labeled C is it's the L63N ASR well. We often refer to it as the Taylor Creek ASR well. That was built back in the 1980s by the South Florida Water Management District. And what we've been doing now, most recently, is working to reactivate those ASR systems. Since it's been a couple of years for one of them and several decades for the other one, we've been evaluating those ASR systems and trying to repair and reactivate them so that they can become functional, hopefully in the next year, so that we can get some immediate relief to the lake and the estuaries. So in addition to reactivating the existing ASR wells, we're also developing a program where we will be constructing some continuous cores. We're going to be using a technology that allows us to drill an entire and obtain an entire section of lithology from about 500 feet below land surface to 2,000 feet below land surface, and to retrieve those cores and look at them at each of those cluster areas to make sure that we do have the hydrogeology that is conducive to ASR. In addition to the continuous cores, at the circles labeled A and B on the map, we've developed an exploratory test program where we're looking at actually building some test ASR wells to see if the wells can be pumped at the rates that are desirable on the order of 5 million gallons a day, and to be able to do some very detailed design evaluations of the concept of constructing some clusters of wells at each of those locations. So while we're doing a lot of the and planning a lot of the hydrogeologic aspects, one of the big elements of ASR facilities is the water treatment component, where the water that's going to be sourced from these wells, it's canals adjacent to Lake Okeechobee, draining the watershed, stormwater, and we've got to treat that water in order to meet regulatory requirements. And there are an entire universe of water treatment technologies that are available for us to look at and evaluate. Amongst them, listed on the screen, are normal mechanical screens, or media filtration like a sand filter at the Kissimmee ASR system, ultraviolet radiation to disinfect the water, and then there's a whole variety of other technologies: ion exchange, coagulation, nanofiltration, and ultrafiltration. What we're doing right now is having an engineering evaluation of each of those technologies and combinations of those technologies, that we can maybe select the most efficient technology, or the most cost-effective technology to meet those requirements. So we're moving forward through a design evaluation of those treatment processes. So those are some of the tasks that we've been working on over the last year when we've gotten the state appropriations. Those are the various things that we have in motion as we speak. So with that, we're going to get right into the science plan, because as we've been moving forward with ultimately reactivating ASR systems and constructing new exploratory wells and cores and looking at treatment processes, we've actually wanted to use, as we develop all of these processes, we actually want to use as our guideposts. We want to use what the National Research Council had found back in 2015 when they evaluated the ASR regional study, right? Back in 2015, when we published that report, we actually had what is ultimately the third evaluation from the National Research Council on the ASR program. And they published their report in 2015. Ultimately, they found, they agreed with the findings of the SERP ASR regional study, that there were no fatal flaws for the precluding the use of ASR in Everglades restoration. And they also recommended that a phased approach should take place as ASR is implemented, and in order to get some early benefits of the program. And while they did make those essential, did agree with those essential findings, they did elucidate on 6 areas of uncertainty, remaining uncertainty, that they thought we ought to address. And very broadly, those areas dealt with future construction, the ways by which future construction and testing should be implemented, understanding phosphorus reduction potential, which is actually something that we observed at the Kissimmee ASR site. It is regarded as an ancillary benefit of ASR, but we did make a significant observation that nutrients appear to be reduced during storage underground. There would also be operations to maximizing recovery efficiency. They wanted to make sure, of course, that the ASR systems are cost effective and efficient. They did suggest or make a recommendation that we continue evaluating disinfection and treatment technologies in order to meet regulatory constraints while also being cost effective, and also including a lot more toxicological and ecological risk assessment. We're gonna talk a little bit more about what their recommendations were about more detailed evaluations and longer term ecological evaluations be conducted. And then, of course, water quality, about the recovered water that comes out of ASR wells, how it might impact the environment, and also how it might impact the aquifer itself while underground. So the science plan that we've developed has been structured to address each of these 6 broad topics. And in order to formulate how we go about doing that, we thought we could use a little bit of help from a panel of experts that we've recognized throughout South Florida. We created an independent ASR peer panel, and consists of five folks. Dr. John Arthur is the panel chair. He's the director of the Florida Geological Survey. Dr. Tom Mismer is an eminent scholar at Florida Gulf Coast University. Dr. Renee Price is at Florida International University. Reed Heil is a research scientist with the Florida Fish Wildlife Conservation Commission. And Dr. Sam Upchurch is retired from University of South Florida. He was the geology department director for many years. And we got those folks together, and we've had 2 workshops with them. We met back in July to kick off the panel and to introduce them to all of the work that we had done for the previous ASR studies. And subsequent to that, the panel has published a report provided to us where they have provided suggestions on how to address those uncertainties that were included in the National Research Council publications. So with that guidance from the peer panel and looking at the remaining uncertainties, what we've done is formulated the following slides about how to address in much more detail each of those 6 broad areas. And for instance, under the topic of the future construction and testing, what the National Research Council suggested is that we did need to take a look at the Avon Park permeable zone, which is in the middle part of the Floridan aquifer. It's actually, we're hoping that we can utilize not only the upper Floridan aquifer for ASR storage, but also the middle portion of the Floridan aquifer for storage. So in order to address that recommendation about looking at the Avon Park permeable zone, we are undertaking the assessment of reactivating that Taylor Creek ASR well. As it turns out, that ASR well is completed in the Avon Park permeable zone. And we've just recently conducted a mechanical integrity test of that well. And the good news is that well is viable. It still has mechanical integrity and can be pumped at almost 10 million gallons a day. So it's a very high capacity well, and we are looking to reactivate that system and resume cycle testing on that system in order to get more information about the Avon Park permeable zone. And also, in order to get additional data from other locations, we're going to be constructing those continuous cores that I talked about associated with the Lake Okeechobee project. And those cores are going to fully penetrate the Floridan aquifer down to 2,000 feet. We will be able to do very discrete water sampling at 30-foot intervals as each of those wells is constructed down to 2,000 feet. And by collecting and retrieving all of that continuous rock, we will be able to do very detailed evaluations of the mineralogy, the porosity, the geotechnical parameters, properties of the rock, and the hydraulic properties of the rock. And in addition to the discrete water quality sampling and water quality analyses that we'll be able to get, we're going to be able to do some geochemical modeling, benchtop modeling, to determine what's going to happen when we take source water, surface water, and blend that, push it through water that's in the aquifer, what kind of reactions are going to take place geochemically, so that we can have some understanding of what attributes that mixed blended water is going to have. Ultimately, all of those cores are going to be slabbed and described and analyzed and ultimately stored by the United States Geological Survey. So they will remain in posterity for any researcher that's interested in learning more about that rock. And these are some pictures of our work at that ASR well, the L63N ASR well. The photograph on the right is what it looks like today. It's been sitting out there since 1986, but it's got mechanical integrity, and we're looking forward to rebuilding surface facilities at that system and get it up and running within the next couple of years. A little bit, some of the photographs on the left are pictures of what the borehole looked like. The upper left picture is what the borehole looked like down there at about 1,500 feet. It had become filled in with sediment and some cable from a previous geophysical logging run. After we got done cleaning it out, the picture on the bottom left is what the borehole looks like now. It's highly open. It's got good porosity and permeability. It's a very high capacity well, and that borehole takes a lot of water. And also in the process of cleaning out the borehole, we were able to retrieve all of that cable that you see on the picture on the right. That's all of the geophysical logging cable that came out of the well when we were able to clean out the borehole. Very successful well. Okay, a little bit more about those continuous cores. The map on the left, you see the yellow dots. Those are the areas where we're envisioning constructing some up to four continuous cores right now, is what our schedule includes. And what we're going to be able to do when each of those cores are collected is not only we're going to be able to retrieve all of that rock that I just described, but we're also going to be able to conduct some geophysical surveys. The picture on the right is a detailed lithologic column of the kind of rock that is recovered from 0 down to 2,000 feet. It enables us to do very, very detailed analysis of the kinds of rock, the kinds of porosity that are in the rock, and they also allow us to run geophysical logs in the well. And those are some of the traces that you see in the middle part of that column are some of the attributes: gamma rays, sonic porosity, density porosity, the resistivity of the rock, the temperature of the rock. All of these things are physical attributes that geophysical logs help us determine. And when we conduct them, they help us figure out where the storage intervals are, where the optimal storage intervals are underground, so that when we build an ASR well, we can fairly well predict that it's going to be a successful well. So these are the kinds of things that actually, by constructing those continuous cores, we actually just get an awful lot of information out of by conducting the geophysical logs. And as I had mentioned, while we're constructing the continuous cores, we're actually going to be able to collect discrete water samples from 500 feet down to 2,000 feet. And the list on the left-hand side of the slide are those parameters that we're going to have analyzed by a laboratory every 30 feet down to the maximum depth of 2,000 feet. Now, in addition to those 30-foot interval sampling analyses. When we get into the depths that we actually think we're going to use for the ASR zones, for the storage zones, we're going to collect samples on the columns for analysis on the columns on the right-hand side of the screen. And as you can see, it's a much more diverse grouping of chemical parameters that will enable us to do that benchtop geochemical modeling that I was referring to. So we will have very precise understanding of what that water quality is like in the zones that we are envisioning for use of ASR. So that's a little bit about what the continuous cores are going to give us. In addition to the continuous cores, as I mentioned, we are also planning on constructing test exploratory wells in 2 areas along the C38 canal. And we call these respectively the C38 North and the C38 clusters. And the maps on the right show conceptual schematics of what those well clusters would look like in groups of maybe between 5 to 10 wells and ASR wells and monitor wells. And this is all very conceptual right now, but what we do have is we do have permit applications in-house at the Florida Department of Environmental Protection to construct the first couple of wells at each of those locations and monitor wells. And by doing those test exploratory wells, we're able to do a lot of evaluations, design evaluations of what those well clusters, how many wells they could be, and how close or far apart do the wells need to be, and what should the piping configuration be, and what does the water treatment process need to look like in order to supply water to those wells. So there's a lot of work that needs to be done when you construct these exploratory wells. And in addition to all of the design work to figure out what the cluster configurations are like, we're also able to develop some local scale groundwater models and to conduct geophysical surveys and perform tracer tests to try to understand what the vagarities are of the hydrogeology of the area, because the hydrogeology is a lot like a box of chocolates. Every site has its nuances in terms of what the water-bearing properties of the aquifer are like. And so when we build these exploratory wells, we'll be able to run several geophysical surveys and tests that will allow us to have a much more detailed visualization of what the aquifer is like at each of these cluster locations. So yeah, we're going to be building multi-level nested exploratory wells and monitoring wells. We're going to be conducting pump tests on the wells. We'll be looking at withdrawing water from the wells and doing a tracer test at each of the locations to determine, again, aquifer anisotropy and heterogeneity. And then from all of those kinds of analyses, we'll be able to conduct some very detailed local scale groundwater modeling. And these are just some graphics of tracer testing. And the idea of a tracer test, once we have the exploratory wells nested with monitor wells, we'll be able to insert a dye into the aquifer, like a food grade dye into the aquifer, and then using the monitor wells, we'll be able to trace where that water goes in the aquifer. I know folks are always interested to know where is the water going when it goes underground, and that's the value of these tracer tests that we will be able to conduct from the test well clusters that we build. In addition, the map on the graphic on the left shows aerially how you can trace a dye looking at above, but also the graphic on the right shows that we can also follow the tracer vertically, and we can determine if there is buoyancy stratification or fracture flow within the rock, that where the water might be moving up or down within the aquifer itself. And all of these kinds of tests allow us to make good design choices of where the wells should be completed and how to design the well field at each of those locations. In addition, once we have done a tracer test and pump tests, and we now know where the water's flowing in the aquifer, we can develop a local scale groundwater model that allows us to run simulations of where the water, how far the water goes underground, and in which direction the water goes underground. So these are some graphics from a groundwater model that has been developed at the Kissimmee ASR system. And the graphic on the left shows a simulation of pumping the blue colored water is the fresh water that would be pumped into the aquifer. And then you see a gradation of colors away from where the wells are, where the water becomes more diluted and is more brackish, like what the water quality is like in the aquifer itself. So it allows you to see what kind of diffusion takes place within the aquifer. And then what you can do is, looking at it from above, you can run simulations as to how far that fresh water will go within the aquifer itself. And in the graphics on the right-hand side of the screen, you see that there were two different zones within the aquifer. There's an upper zone at the very upper part of the Floridan aquifer. That's the flow zone. And then deeper within the upper Floridan aquifer is the graphic on the right. And those lines that you see, the yellow, the green, and the purple lines, are how far the water goes away from the well after it's pumped in for 9 months, 6 months, 9 months, and 12 months. So you can see here that by using those monitor wells and a groundwater model, you can really tightly define where the water is going and ultimately where it's not going by use of a local scale groundwater model. So there's no question that using the wells, groundwater wells, ASR wells, and the monitor wells that are associated with it, you can get very specific information at a point, at one point in a map. And as you might imagine, there's a lot of areas beyond where there are actual wells. And so to try to visualize what the rock surfaces are like in between the wells and beyond the wells, we can utilize geophysical surveys. And there's a whole variety of geophysical surveys that the National Research Council suggested we try to do, including cross-well tomography and vibrational seismic testing to determine if there are faults in the formations or disturbed zones within the formations. The graphic on this slide shows what a two-dimensional seismic line looks like in the area about a mile or two away from the Kissimmee ASR Pilot Project. And the graphic on the left shows what an uninterpreted view of that seismic line shows at depths near 1,000 to 2,000 to 3,000 feet. And then the same graphic is shown on the right, and that shows an interpretation of what the geology is like as a result of those various seismic traces. And you can see here that there are zones that deep within the strata are broken up by faults or fractures. It looks like there are some disturbed zones. And we can use this kind of analysis to decide or help us decide where are areas that it looks like the conditions are favorable for ASR and areas that we probably ought to stay away from because the geology is a little bit more complex and might not yield very efficient wells. So the group right now, what we've got planned is to try to determine which of these various geophysical technologies we can implement in the areas of the test exploratory programs, and a variety of different technologies: electromagnetic induction, resistivity, vertical seismic profiling, cross-well tomography, magnetotellurics, three-dimensional imaging, and microseismic monitoring. They are all currently under evaluation to decide which combination of geophysical tests we want to run at each of the exploratory test well locations. So all of the last 5 or 6 or 7 slides I showed you are all of the things that we're going to address that first broad topic of future construction and testing. Those are all the various things that we intend to integrate into the science plan as we roll out the ASR program. The next topic, the next broad topic, was about understanding phosphorus reduction. And as I had mentioned, when we cycle tested the Kissimmee ASR system, we monitored the concentration of phosphorus in the water going into the ASR well and coming out of the ASR well during each of those successive 4 cycles. And the graphic on the right shows you what the black bars are: the concentration of phosphorus that was pumped in the water that was pumped into the ASR well during recharge, and the white bars are the concentration of phosphorus that in the water that was recovered from the ASR well during each cycle. And frankly, we were certainly not expecting this degree of nutrient reduction that we did observe, and not that we're not pleased with it, but we certainly need to do testing to try to understand the mechanisms by which that nutrient reduction is taking place. Is it a combination of a physical process or a mineralogic process, or are there microbiological components to the aquifer that are metabolizing phosphorus? So what we've done is we've created a program. We've been scoping a program with the United States Geological Survey, Dr. John Lyle in St. Petersburg, to develop a series of flow-through experiments. And what we're going to be doing is we're going to be taking the cores, sections of the cores, the continuous cores that we're going to be collecting in the coming year, and we're going to be giving them to Dr. Lyle, and he's going to insert them into columns, and he's going to begin trickling water through them and monitoring the reactions that take place as a result of the water, the source water interacting with the organisms and the lithology of the rock. And we're hoping that what he can do with his work is to help us determine if we can actually count on nutrient reduction. Can we dependably rely on ASR to be a water quality improvement component to the system? And this is a diagram of exactly how Dr. Lyle is going to be conducting the core experiments, and the graphic sort of shows the variety of different columns that he's going to use. One of the columns, and if you can imagine, this is going to be a core maybe 3 inches in diameter of rock, maybe 12 to 18 inches long. It's going to be put into a plexiglass tube and glued into place, and then water is going to be put in the top of the tube. It'll allow the water to trickle through the core, and he'll be able to collect water chemistry samples, biological samples, gas samples of the water as it makes its way through the core. And so one core column is going to be composed of the actual core that's collected from the continuous coring operation. One of the columns will be ground up core material, the same rock, but ground up. The third column is actually going to be ground up core material where he's actually going to grow the community of organisms that live down in the aquifer. He's going to be able to generate a community of organisms to look at a core that's got growth on it already. And the fourth column is going to be a series of silica glass beads, just as a control, a laboratory control example. And so these core analyses are all going to be subjected to all of the analyses that are listed on the left-hand side of the slide: microscopic evaluation, biofilm production rates, organic carbon characterization, microbial community biomass growth, biogenic gas production, diversity and function of the microbial community, calcium carbonate modeling, precipitation, mineralogic evaluations, particle size analysis, and zeta potential. These are all the various individual tests that Dr. Lyle will be conducting on these cores and his column studies. And to address the topic of operations to maximizing recovery, what we're primarily going to be looking at doing is creating a buffer zone within the aquifer. And what that concept is rather than say pumping 100 units of water into the aquifer and then recovering all 100 units out of the aquifer, the idea is to not recover all of the water during each individual cycle, but to leave some of that water underground. The idea being that that water that's left underground can create a buffer zone. It will be a blended mix of the water that's in the aquifer and the fresh water, but that allows you to create a zone within the aquifer for the next cycle. When the next cycle of recharge takes place, that buffer zone water actually enables you to keep the formation water, the brackish formation water, away from the ASR well. And by creating that buffer zone, you can actually drastically increase the recovery efficiency of each individual well. So it'll be that style of cycle testing that we're actually going to be conducting when we do begin the testing of the exploratory wells and when we reactivate the Kissimmee ASR well and the Taylor Creek ASR well. And there was also some uncertainty about placing ASR wells to address or to minimize the impacts due to the ecology or the environment within the lake and within the canals. So what we intend to do when we do recover the water is we're going to be conducting some plume modeling so that we understand when we route the recovered water back into the surface environment, we'll be able to monitor and predict where the thermal effects are and what water quality variations may take place, what dilution and what kind of effects are going to take place when that water is recovered from the ASR wells and placed back into the environment. And what we're trying to do by modeling that is we certainly want to minimize the impacts to the fish community, manatees. We don't want to have any thermal effects. And what that will also enable us to do is to design the discharge structures so that we create the minimal amount of discharge plume that will be routed back into the environment. And treatment technology is another area that the National Research Council wanted us to make sure we focus on, and it's actually one of the most important ones from a cost perspective, because treatment technology, building water treatment plants, is a very expensive thing. It's probably one of the largest cost drivers for constructing and operating ASR systems. So we need to be very careful about which treatment process we select when we're designing these ASR systems. So right now we've got an engineering firm, Stantec, has been providing us with an evaluation of the universe of treatment processes that are available to us. And we've completed the initial phase of treatment technology. Right now, what you see, the graphic on the slide, is a costing analysis that they did for years of operation, a 50-year life cycle cost of various alternatives, a combination of nanofiltration, ultrafiltration, coagulation. Each different process has a variable life cycle cost. And we're right now trying to determine which are the optimal processes that we want to go forward with, conducting some more detailed evaluations. And we're actually having an independent technical review of this initial investigation to make sure that we've got a lot of eyes on this decision process. No question about it, treatment technology is a very fundamentally important thing when we design these ASR systems. And like I mentioned, the other thing that we're going to be able to do is looking at these treatment alternatives when we do collect the continuous cores, and we do have that water quality information from the discrete sampling, we're going to be able to run some benchtop mixing models to determine exactly what is going to be the water quality that occurs within the aquifer and what ultimately will be recovered from the aquifer. And that's going to help us, again, high grade and determine which treatment technology is the most effective on minimizing any bad attributes to the recovered water or maintaining high water quality within the aquifer itself. And the other aspect of this treatment process is stuff that we've actually, again, with Dr. John Lyle at the USGS, Dr. Lyle has conducted tests on surface pathogens that are in normal surface water. And what he's done is he's created flow-through mesocosms where he's taken populations of those surface organisms and subjected to water from the Floridan aquifer. And he's been able to determine exactly how long those pathogens live while being subjected to water that doesn't have any oxygen in it. It's an anoxic, aerobic, reducing water, aphotic, there's no light within the aquifer. And what he's been able to do is essentially create what I call death curves of aquifer. It's the rate at which these pathogens, surface pathogens, stay alive when they're emplaced within the aquifer. And Dr. Lyle has determined that there's about a 5 log reduction in populations that normally take place over about a 60-day period. And he's been using Escherichia coli, bacteriophage for the tests. Most recently, he's done the same experiments using Cryptosporidium and enterovirus, and all of the results basically show the same kind of inactivation rate. So this is important because ultimately what he is documenting is that there may not be as much of a need for disinfection on a surface facility because the aquifer itself, the conditions within the aquifer, actually provide a degree of disinfection when those organisms are placed underground. So his work has been truly fundamental in determining that. There's really very few researchers on the planet that do what Dr. Lyle does. And ultimately, when we get the exploratory test well results, and we will be able to do those groundwater models that I talked about, the local scale groundwater models, what we will be able to do is to couple his Dr. Lyle's work on the inactivation rate, and for instance, a 60-day, how far the water goes over a 60-day period. We can actually couple the inactivation rate with a travel time contour interval to be able to determine exactly how far that water travels in a 60-day period, and where there are actually live microorganisms in the aquifer and beyond which there are not. So that is a lot of the hydrogeologic stuff that those first couple of broad areas. Those are the proposed scientific studies that we're intending to do in the science plan. And now I'm going to switch. I'm going to hand the mic over to Anna to talk a little bit about the ecotoxicological evaluations that are now included in the science plan. So,
thank you, Bob.
Anna?
Yep, I'm here. Thank you, Bob. So as the NRC panel recommended, we plan to conduct additional bench scale chronic toxicity tests, mesocosm experiments at the points of discharge, and long-term in situ bioaccumulation studies. For the bench scale chronic toxicity tests, we propose to use the same standard toxicity tests as used in the NRC pilot project in the past, to study the effects of recovered water on survival, reproduction rates, and growth of indicator algae, zooplankton, amphibians, bivalves, gastropods, and fish. Additionally, as the panel also recommended, we'll use recovered water from different ASR wells and locations in the test, and we will consider longer storage time and greater storage volumes. We plan to conduct additional modeling at larger and smaller scales to evaluate effects of the recovered water on water quality in downstream ecosystems, and use the results of the modeling to design lab and field studies. Because the recovered water might have elevated mineral content and hardness, this can potentially affect organisms occupying saltwater areas of the Everglades, such as, for example, periphyton, invertebrates, or fish. Therefore, we will conduct additional modeling to test the effects of the recovered water on saltwater areas of the Everglades. And in addition to the lab test, we will also use the results of the modeling to set up mesocosm experiments near ASR point of discharge to test the effects of the recovered water with elevated mineral content and hardness on selected organisms occupying saltwater areas of the Everglades. We also plan to conduct longer term, meaning from several months to a few years, in situ bioconcentration and community composition studies using periphyton, mussels, apple snails, and fish. The studies could begin before the ASR operations start and continue during the recovery and discharge periods. The potential study sites include the lower Kissimmee ASR locations that Bob was describing. And periphyton is a fundamental part of the Everglades food web and primary food source for fish and invertebrates. And it can absorb nutrients, toxins, and minerals from water, and their species composition changes relatively quickly in response to changing water quality conditions. So they're very sensitive to changing water quality conditions, which makes them really great bioindicators. So we plan to look at the concentrations of minerals and toxins in their biomass and study changes in their species composition. Apple snails are also very important components of the food web. They're important food source for the endangered snail kite and other birds, fish, and mammals. Therefore, we will be looking at the bioconcentration of heavy metals in these organisms. That will give us information on potential transfer of metals through the food chain to apple snail predators. And mussels will be deployed in cages at the same locations where we will be collecting periphyton and apple snails from. Additionally, we'll be looking at the impact of temperature alterations on fish spawning. So the plan is to look at the common fish species, like for example, black crappie, which is an important commercial species that spawns in the areas that might get affected by the recovered water. Next slide, please. So we also plan to incorporate all the chemical toxicity, bioaccumulation, and other data collected throughout the study period into a comprehensive assessment of risks to ecological receptors based on the conditions expected in a range of ecosystems modeled using the data. As the NRC panel recommended, we plan to use a population-level approach to modeling the impact of ASR recovered water on biological communities. We'll also use the expected operational parameters of the wells in that risk assessment. We plan to coordinate with stakeholders which organisms and variables are important and should be included in the risk assessments and also our studies. We'll follow the new SCPA guidance on conducting ecological risk assessments. Back to you, Bob.
Okay, thanks, Anna. I believe that the next portion of the discussion is actually going to be about water quality. That's within the aquifer and recovered water. And for this part of the conversation, I'd like to introduce Dr. June Maricki. June, are you there?
Yes, I am. And I've been answering questions that were proposed as the other speakers continued, and I can see we have a good number of geochemically inclined people on this call. I only have a few slides because you know I can go off on this stuff for a long time, and we don't have a long time left. So basically my slides are structured with the top bullet being the uncertainty that was identified by the National Academy of Science and our peer review panel. And then the bullets beneath that are kind of the things we've done. And then the final bullet at the bottom of each slide is really how we're going to approach answering and reducing these uncertainties. And the next few slides are strictly with groundwater quality, geochemical reactions, and surface water, groundwater, and rock interactions. So one of the main uncertainties as identified by the National Research Council and others is to understand the impacts of different compositions of source water on the long-term redox evolution of the aquifer. And those of you who are practitioners know those Florida aquifer wells are pretty stinky due to the hydrogen sulfide, so that these are very reducing systems. and you're introducing surface water that is often saturated with dissolved oxygen, so that you have this, how does the redox condition in the aquifer react to that, and how long does it occur? We looked at that a lot at the Kissimmee River ASR system back in the day. The driving criterion really was the arsenic groundwater quality criteria of 10 parts per billion. That was really the driver for a lot of our water rock interaction work. Now, we clearly understand that there are water rock interactions that occur when you introduce this high DO, high dissolved organic carbon, nutrient-rich water that can be warmer or colder than the aquifer into an aquifer. And so the way to start characterizing completely those water rock interactions at any ASR system, not just ours, is to have a very robust sampling program and a good monitoring well network. And in the past, we've worked at one ASR well ASR system. So you have an ASR well surrounded by a network of monitor wells. In the projects that Bob Verastro has presented so far, we're scaling up so that we will have multiple ASR wells, and these will recharge and recover, and the monitoring network will expand around these greater number of ASR wells. So it's really going to require a robust monitoring program to understand how groundwater quality changes over space, away from the ASR well, and over time. Next slide, please. Okay, the next uncertainty to be recognized. Did we go too far? Can we go back one? Oh, no, you're right. Okay. Along those lines of scaling up in our ASR systems, both in space and time, not only are we expanding the ASR systems to be multiple recharge and recovery wells, but we are also using these 5 million gallon per day ASR wells over longer recharge, storage, and recovery durations greater than a year. We're going for longer term storage so that we can really contribute to lake level, ultimately to lake level attenuations. Now, when we had a one well ASR system, we could demonstrate through our monitoring well network how far away arsenic persisted in space and time. The two figures on the left are monitor well data sets, one at 1,100 feet away from the ASR well, and the lower one at 2,350 feet away from the ASR well. And you can see in that bottom figure, the arsenic concentrations are well within the drinking water quality criteria. So in a single well system, the maximum extent of the so-called ASR bubble is between 1,100 and 2,300 feet. Well, this is going to go bigger as we expand to multiple ASR wells and storage over longer durations. And it's just another reason why we need to have a robust sampling program to reduce this uncertainty. Okay, next one. The panels identified another uncertainty that we work much more clearly to define a buffer zone, which is a zone of mixed water quality between native groundwater and recharge water. There are certain constituents that we can develop this buffer zone in order to limit certain constituents coming up into surface water impoundments to be discharged into the environment. In particular, sulfate concentrations, although the sulfate is at concentrations below the drinking water standard, there is a concern that increased sulfate, if it's discharged into surface water bodies and hence shallow sediments, that can stimulate mercury methylation through a long series of geochemical and microbiological reactions. So the best thing to do is to keep the sulfate in the aquifer, and we can do that by developing this mixed zone. And the way you develop that mixed buffer zone is to have an incomplete recovery volume. So you start leaving a little of your recharge water in the aquifer, and then during your subsequent recharge event, displace that away from the ASR well. And if you do that over a couple of cycles, you will develop that buffer zone and keep those constituents of concern in the aquifer. Next slide, please. Okay, this again goes along with the sulfate sources and what the risk is of putting sulfate in surface water impoundments. For the ASR regional study, there was a pretty involved surface water modeling effort to track certain constituents, particularly sulfate, in surface water once it was discharged from the ASR systems into Lake Okeechobee, and that water moved south. And so we do, if you look at, this is just a representative output of the modeling, but the sulfate concentrations, if you look at that lavender color line, could possibly be elevated during discharges into surface water impoundments, because native groundwater in the Florida aquifer has higher concentrations of sulfate than does surface water. So we know that this could happen. We probably, the best response to moderating sulfate concentrations in recovered water is to complete and develop that buffer zone. Next slide, please. Okay, another one of our panelists also identified that we should be aware that some areas of South Florida, or some portions of the upper Floridan aquifer in South Florida, have high naturally occurring concentrations of radium and radium isotopes. And so the Floridan aquifer is shows these distinctly naturally occurring concentrations, mostly in Lee County, Charlotte County, and along those southwest coastal counties. There, the source of the radium is the phosphorus lags at the base of the Hawthorne group. And through a long series of radioactive decay mechanisms, from uranium that is in high concentrations in the phosphate, or uranium in high concentrations in the phosphate, the radium daughter isotopes ping out, and then they remain dissolved in groundwater. Now, radium isotopes are not particularly cheap to analyze, but there is a proxy constituent in gross alpha that is commonly used to screen out or screen for high concentrations of radium. When gross alpha concentrations exceed, I believe, 15 picocuries per liter, that suggests that you should start looking for your isotope concentrations, your radium isotope concentrations. So this is a known phenomena. The South Florida Water Management District has a pretty robust regional Floridan aquifer monitoring program. And the areas where radium concentrations are high are fairly well known. But be that as it may, radium isotopes can be measured easily in native groundwater. So even before ASR systems are constructed, you'll know whether you need to be concerned about the presence of radium. Next slide, please. Okay, now that's the end of the geochem portions. Michelle, I believe you're going to carry the baton now?
Yes, I am. Thank you, June.
Thank you.
So the way the science plan report is structured is it includes a chapter on each general category of uncertainty, which Bob, Anna, and June just presented earlier. The report also includes an additional chapter on project sequencing and data management. So although this doesn't correspond to a specific National Research Council uncertainty, we did receive some comments from our peer review panel related to reporting and data management. So we thought it was important to include a chapter on that within the science plan. So as recommended by the National Research Council, implementation of ASR wells will proceed in a phased approach and will include continued monitoring and research activities as we proceed with construction activities. Some of the following slides include graphics on project phasing and where we're addressing those uncertainties as the project proceeds. The project sequencing and data management section of the report also includes information on science plan workshops. The team is proposing to conduct annual science plan workshops in which we will be discussing results of ongoing research and monitoring activities and also identifying areas that may require further research as the ASR program progresses. The purpose of these meetings is to provide an open forum in order to discuss the results of research done to date and to provide transparency in identifying future research monitoring and modeling needs. These workshops will be open to the public and they will provide an opportunity for the public to make comments at each workshop. This chapter of the report also includes a section on data management. Obviously, what's been presented today, we're proposing quite a bit of data collection of varied data types. Some of it's water quality data, some of it's modeling data, some of it's seismic data. So the comment that we received from our peer review panel is that the data need to be organized, quality assured, maintained, and curated, and that the data should be accessible and usable by any interested stakeholder. The ASR team concurs with this, and we're committed to making the data collected as part of the science plan available to any interested parties. A data management system already exists for data collected in the SERP program, so the team is proposing to use existing data management tools in order to archive the data collected under the ASR science plan, including Morpho, Metacat, and DB Hydro. Morpho and Metacat are primarily used for ecological monitoring and research data. Morpho packages together different data types, makes them searchable, and provides long-term storage of the data. Metacat is a database for scientific data. And once a package is generated and stored, the data become accessible via a web browser. And DB Hydro database is a database that many are already familiar with. It's the district's public database that stores meteorologic, hydrologic, and water quality data. And the DB Hydro browser allows users to query and generate a summary of data for a given period of record. A separate document will be developed to address the data quality assurance objectives for the specific types of data that will be produced for the science plan. These data quality objectives for each sample or data type will describe the quality assurance expectations for each type of data and each type of study. Next slide, please. This figure shows how the different components of the project will address the National Research Council uncertainties. Within each major category of project progression, which are shown on this slide in blue, that they show the different phases of the project and anticipated schedule for implementing that phase of the project. Then within the multicolored bubbles underneath or above it, that shows the different studies that are being proposed as part of the science plan to address those uncertainties. So this shows the different project phases that will address each of those 26 uncertainties as identified by the National Research Council. And this goes to show that during each phase of the project, some of the phases of the project are running concurrently, and there is some overlap. Some of the uncertainties will be addressed in multiple phases of the project as well. Next slide, please. This table shows the same information that we showed on the last slide. It just shows it a different way. So the column to the left shows the 26 different NRC uncertainties in that column. And then it shows the expected timeframe or project phase for initiating the research activities to address each of those uncertainties. And again, some of these studies, as you can see, some of these studies last through multiple phases of the project, and some of the studies will be concurrent. It's important to note on this that the timeframes that are provided here are tentative in nature, and the schedule for the research as well as the construction activities could be influenced by factors including funding availability as well as obtaining regulatory approvals as we proceed with construction activities. Next slide, please. In the 2008 ASR program interim report, the ASR team used a report card in order to track progress of the project. So our peer review panel recommended development of a similar report card to represent the progress made towards addressing the National Research Council recommendations. And the purpose of this is for project managers to track the progress of the various science plan studies, but it's also useful for communicating that information to stakeholders that are interested in science plan research. So this slide shows an example of a report card for the science plan, highlighting each of the National Research Council comments and progress towards addressing each of those comments. And the intent of the team is to present this ASR report card at those annual public workshops in order to communicate progress towards addressing each of those uncertainties. Next slide, please. So this slide shows the next steps in the ASR Well program. So as was mentioned at the beginning of this meeting, the draft ASR science plan is currently undergoing technical editing in preparation for the upcoming reviews that are scheduled to begin in early January. Once the report is through final technical editing, the report is going to be posted on the Water Management District's ASR website. And the link for that website is provided when we get to the next slide. The report will undergo public review and a technical review by the Army Corps of Engineers. Both of those reviews will run concurrently. On the construction side of it, construction of continuous cores at 2 locations are anticipated to begin in the near-term timeframe, beginning at L63N and then followed by the L63S location. Those cores are going to be analyzed for mineralogic and geotechnical properties. And then, as Bob had talked about earlier, we're going to be continuing the treatment technology evaluation. Some research that is going to be conducted in the near term is column studies of nutrient reduction plugging potential. That research will be conducted by USGS. Additionally, we will be initiating construction of exploratory wells at the locations along the C38 canal, the C38 North and the C38 South locations. And as Bob had mentioned earlier, we're working to reactivate the existing Kissimmee ASR well, as well as the L63N ASR well. And then another activity we're looking at the near term is the team is starting to develop a plan for those ecological assessments that Anna discussed. And again, the draft ASR science plan will be available for public review in January 2021. And Bob, if you go to the next slide. So this slide shows the district's website where that ASR science plan will be posted when available. And with that, I know the team has been responding to questions as they've arisen, but I wanted to turn it over to Jennifer Gent, who's going to go through some of the remaining questions and answers, as well as open it up for public comment.
I think Jennifer is having technical difficulties again. So this is Liz Kaneha, and I'll be taking over at this point. So as Michelle had said, we are answering some of the questions, and in effort to save time and let everybody provide public comment, I'd like to just go to the raise your hand feature And if you have a comment, I'll call on your name and you'll have approximately 2 to 3 minutes to give a comment on the workshop. So the first hand I see raised is Peter Simmons. Peter, please unmute yourself and state your comment. Hello, Peter, are you there? Okay, I'm gonna go to the next. Oh, yes, we hear you. We hear you, Peter. Oh, there you go. It looks like you're unmuted right now. Okay, I'm going to move to the next person. Newton Cook, please state your comment.
Thank you very much. This is Newton Cook. Couple of points. I've supported these ASR wells from the day they were proposed a long time ago. I'll be honest, I didn't think it would do a whole lot for the lake, but I knew that with the Kissimmee River Restoration Program, there were going to be droughts, and we needed to keep the sheet flow in that $1 billion restoration program and not let it go dry. The second point is a simple question. When we spend all this money, how many discharges, damaging discharges to the Caloosahatchee and the St. Lucie will be stopped? The answer to that question is 0. Not a single one will be stopped. There's no capacity at the rate of flow necessary to prevent the water coming down the system and overfilling the lake. Number 3, the water with arsenic was the first thing we were worried about. Now I hear today radium. The cost involved on a large scale of the original plan of 330 some odd wells was pretty well abandoned some years ago in the discussions at RAC for these very same reasons. I'll ask the question again. Are we trying to stop the discharges to the St. Lucie and the Caloosahatchee to keep the lake from overfilling with up to 30,000 CFS flying, flowing into the lake from the north? If the answer to that question is yes, that's what our intent is, then there's only one way to keep the water from going into the lake from the north without all this expense, without all these studies, and that is deep injection wells. 300 deep injection wells will simply take 9,000 CFS out of the Kissimmee, put it in a saltwater river, 3,000 feet down, no testing required. The DEP's already approved it. And it goes to the same Atlantic Ocean that the water is going to now, but it's destroying the estuaries. I would remind you, we're trying to save the discharges to the estuaries and to keep the health of the lake. Thank you very much.
All right, thank you, Mr. Cook. Next with the hand raised is Nyla Pipes. Please state your comment.
Good afternoon, Nyla Pipes, One Florida Foundation. We are in support of the ASR wells because we recognize that without ASR, the rest of comprehensive Everglades restoration just simply doesn't work. That's why they were a part of the plan to begin with. And I really appreciate all the in-depth scientific conversation. I think it's incredibly important that the public tune into these meetings because there's this, I don't know, kind of idea out there that we're just going to plunk some wells down without any thought for the consequences. And what you guys have demonstrated with these ongoing various meetings and workshops that have occurred regarding ASR is that this is a very scientific, well-vetted, slow implementation process. And I think that's incredibly important because we have to know what's going on. And I just wanted to commend you for all of the hard work you've done. And, you know, we stand here beside you to help communicate to the public why this is a great option to look at for a number of reasons, not the least of which being helping out both the lake and the estuaries. Thank you so much.
Thank you, Ms. Pipes. Next with their hand raised is Ernie Barnett. Please state your comment.
Hi, my name's Ernie Barnett. I'm with the Florida Land Council and had the good fortune to work on the Comprehensive Everglades Restoration Plan throughout the 90s. As a member of the Florida Department of Environmental Protection, I was actually the lead state person on the restudy team. And, you know, it's widely documented in the restudy that the restudy plan in its entirety just simply didn't work until we added the ASR well component. So I'm a firm believer that the ASR wells are an integral part in overall Everglades restoration. And then most importantly, the ASR wells are really the only tool that we have that would really provide significant reductions in estuary discharges. The Lake Okeechobee Watershed Protection Plan, when you look at the future without project condition, by adding the 80 ASR wells, you see an overall net reduction in the frequency or the months over the 40-year period of record of discharges go all the way down from a pre-CERP baseline of 71 high frequency discharges, high discharge events down to only 19 to the St. Lucie estuary. And that's a phenomenal reduction of about 71% and a 48% reduction over the future without project conditions. So these are integral to our ability to actually stop harmful discharges to the estuaries. I do want to make one comment though, and I think the stepwise approach that you're laying out in the science plan is prudent, but I also think a lot of the issues that have been raised by the National Academy of Sciences would simply be addressed through the very stringent and protective regulatory UIC program that the Florida Department of Environmental Protection implements. And those stringent protections that are required in order to construct, design, and build and operate an ASR well are extremely protective in Florida. And then lastly, on the issue of scale, albeit 80 wells is a large scale, it's really not a large scale implementation when you're implementing it in clusters of 10 wells very widely dispersed throughout the landscape. It's not an uncommon, unprecedented amount of clustering of wells are already happening in Florida. We have the Peace River ASR facility that's been in operation for several decades. I believe there's 25 wells or more in that cluster. So this is a really obtainable, affordable way to provide a significant amount. I believe the Lake Okeechobee Watershed Protection Plan, the ASR wells constitute about 90% of the storage north of the lake and 448,000 acre feet. So continue the good work, continue the getting the science and data lined up right. But I also think a lot of the prudent implementation will come in the phased approach and into clusters of 10 wells being implemented at a time. And I think the level of funding that you're receiving from the state of Florida matches up very closely with a very prudent and phased implementation schedule. Thank you for the opportunity to comment and appreciate all the good hard work that was done by those who presented today.
Thank you for your comment. Okay, next up we have Michael Collins.
Hey, good afternoon. Kudos to Bob and the entire team. Great presentation. Really, really good work. I mean, real hardcore, well-directed, well-managed science. Like Ernie Barnett, I was in the room when Stu Applebaum rolled out the original plan for ASR as we were doing the restudy. And I am unaware of any human endeavor in the many years since then that we've been involved that's had more scientific research, more review of that scientific research, more pilot projects, more review of pilot projects, potential potential issues, potential solutions. We put a man on the moon with a lot less effort than this. But on the other hand, it's prudent and wise, as Ernie said, to do a lot of this. But, there've been a whole lot of reviews. I've sat through pretty much every single peer review panel that's been done on this. And at some point, the legislature and the people in Congress that give us this money are going to want some results. And I think the science that's been done is cutting edge, some of the best stuff I've ever seen. Dr. Lyle's work was an absolute shock when I first saw it, but it's all good stuff that's come out of this. But at some point we need to move forward. We need to, get the water for the Everglades out of this. Just like we planned back when Stu introduced it to all of us. So again, kudos for all the great work. Thanks for the opportunity to see it all, and I wish you all well.
All right, thank you, Mr. Collins. Next up is Mark Perry.
Yes, thank you. I've followed ASR ever since the beginning as well, and the ASR projects that are being proposed, and watched the regional study had to reduce the total number of ASR. We were dependent on Lake Okeechobee ASR 200 wells, and now it's down to 80 or less. And those that are being proposed in the Lake Okeechobee watershed project, the 80 there are not really going to be significant in reducing at all the discharges to the northern estuaries. At only about 7.7 cubic feet per second per well, even times 80, that's nothing. 600 CFS, that's really incredibly inept to try to hold back any discharge events with ASR wells. There's a lot of storage that needs to happen north of the lake, but counting on 440,000 acre feet of storage, which is pumping 24/7, 360 days a year, those 80 wells is not going to really provide that true storage capacity you need north of the lake to minimize those lake inflows and therefore minimize the discharges to the estuaries. But you've been pressured into getting this 50 million each time from the legislature to say you got to implement a component of the Lake Okeechobee watershed project, and you're doing it through the ASR program. And I know there's been a lot of work. I've followed all the science through the whole thing, but ASR wells are not really the success that we need. They're not going to do the job that we need to really stop or minimize the discharges to these estuaries. And it's not going to really help the lake at all. Sure, they're useful in some areas, and they have been used and shown somewhat successful in recovery on certain ones, and others they're not so good at recovery. And there's a lot of other problems with ASR, and particularly, and we're just really kind of minimizing some of and you're trying to maximize some of this value of using ASR wells in these projects. And it's not going to be the success that you think you're going to get. Thanks.
Okay, thank you for your comment, Mr. Perry. We are at our 2:30 mark, but I want to go ahead and continue with public comment. We only have a few more hands raised, and I just want to give everybody an opportunity to state their comment. So please bear with us. Next up is Miss Jackie Thoreau-Lippish. Please state your comment.
Good afternoon. I just wanted to thank staff, especially Mr. Bob Vrasto. He does such thorough work. And also thank you to everybody who made comments. Have a good afternoon.
Thank you for your comment. Next up is Mr. Thomas Van Lent.
Yes, thank you. I'm Tom Van Lent from the Everglades Foundation. I just wanted to also echo a lot of the comments. The progress since the July workshop to now is really astonishing. And I want to congratulate the team for basically using the National Academy's review of the regional study as the roadmap for addressing the questions to determine the viability of ASR. And it's pretty clear that you all have thought a great deal about the most important elements, in particular the fate and transport sections was really evidences a lot of thought. And the ecotoxicology analysis that you proposed, where you actually get a quantitative risk assessment, that is really a major step forward. I also want to thank you that even I was hoping that there'd be a public engagement component, and your inclusion of an annual workshop and making the data available is also extremely important. So thank you. So I'm just saying that as a science plan, I think we look forward to actually reading it and give you specific comments on the technical details, but it certainly does look like you have given this a lot of thought and that you are on the track to get the information that we all need. So I wanted to just say that thank you and congratulations. I think this is a big step forward, and we look forward to reading actual science plan and giving you specific recommendations on that. So thank you.
Thank you for your comment, Mr. Van Lent. Next up, we have Eve Samples. Please state your comment.
Good afternoon. I'm Eve Samples, Executive Director at Friends of the Everglades. I want to echo the thanks to staff for the really extensive work and thorough reporting on the implications of ASR wells. You explained it well, not just for folks who have been entrenched in this for decades, but also for more recent observers like myself. I think you identified really critically important questions that remain unanswered, and they remain unanswered more than 2 decades after widespread use of ASR wells were envisioned for Everglades restoration. So these long-lasting concerns and the scrutiny is reflective of the legitimate problems that remain about this technology. So including, just to highlight some of your presentation, drinking water impacts. We at Friends of the Everglades are very concerned about risks posed to water supply, some of which may not be fully known or understood for years or decades. We're not convinced that's worth any incremental benefits that the wells would present. Also ecosystem impacts, especially toxicology and pathogen risks. Limited capacity for reducing discharges from Lake Okeechobee to the St. Lucie and Caloosahatchee estuaries. If we're talking less than 8 cubic feet per second per well, that's really nothing compared to what the estuaries are getting even this year, which was not one of the worst years, but not a great year either for the estuaries. A couple more concerns that we see: ASR wells north of the lake don't really help deliver water to the southern Everglades during dry months. They're certainly not the most efficient way. And the cost, of course, is a concern, not only of construction, but ongoing operations. So bottom line, is this a worthwhile investment when so many uncertainties remain? We think the answer is no. We don't think it was worth the $100 million the Florida legislature has already allocated. And we don't support further investment in this technology, even as we appreciate staff's transparent and thorough review of it. So we'll be watching the pilot project with interest and look forward to continued objective analysis on the performance. Thank you.
Thank you for your comment. That concludes our comments portion of the presentation. It looks like there's one question that is still open, and it seems like it's stuck in the queue. So I'm going to go ahead and read it. It's from Kimberly Mitchell. In one of your responses, you suggest 80 wells combined with WAF will reduce the discharges to the St. Lucie estuary by 17% and the Caloosahatchee by 36%. What is WAF? What does it do? What does it cost? To summarize a response, a wetland attenuation feature is a flow-through wetland used for surface water storage to attenuate peak flows in stages in adjacent areas when the Lake Okeechobee stage is above the ecologically preferred stage envelope. Although a WAF provides above-ground storage like a reservoir, water levels may be suitable for growth of wetland vegetation due to the water depths, typically realized through operation of the facility. The cost of the WAF is presented in Appendix B of the Lake Okeechobee Watershed Restoration PIR EIS, and that can be found on the Army Corps' website. The estimated cost of the WAF is $1.28 billion. And I believe the rest of the questions were answered through Zoom. So I think that concludes our meeting today. We encourage you guys to visit our website, which is shown at the link below. And that's all we have today. Thank you very much. Have a great day.
Thank you.